In this video, I wanted to go over an example or two on how to determine the rate law from rate data. So you have this initial rate of reaction given two concentrations of reactants, and determine it once the concentration of a reactant is changed, how does that affect the rate? Okay, and that will help us determine whether or not it changes with regard to first order or second order or zeroth order, if that happens to be the case. So let's take this data that I actually got from one of your ALEKS topics. So if you have, let's start with the H2. Let's start with H2 here, and I'll use red for H2. So if we're holding N2 constant, okay, if we're holding N2 constant, in order to get from 2.10 to 0.934, right? That is a reduction. Once you divide, let's see, we're going to divide 2.10 divided by 0.934, all right, and that gets us to, doing on my calculator here, we get 2.2483. So this is just the ratio between the two. That's all that is. So now we're going to look over to the rate of the reaction after we change the concentration of H2. How does that affect the rate here? So we're going to take the same ratio, 28.0 divided by 12.5. Again, just doing it on my calculator real quick to get to 2.24. Okay? So when I look at this, I could say if I take this to the power of 1, I do in fact have what the rate would be, right? So so it must be first order with respect to the hydrogen. So we have rate, let's go ahead and start writing it out here, our rate law, go start writing our rate law out. We have K, it's little k right there, concentration of N2, raised to some power x, we don't know yet, and concentration of H2 we have determined will be an exponent of 1, right? So if you take this number right here, right, this number to the power of 1, you get how the rate will change. Now let's do the other reactant here. Okay, so if I erase all of this, and this is all H2 stuff. If I erase this to do some N2, erase, erase, erase. Alright, so now let's pick another color for the N2. Let's do blue here. So if we're going to hold, for N2 will be blue. So if we're going to hold the H2 constant, we'll do the first two experiments here. So if you have 1.55 divided by 4.65, that gives you, on my calculator, 0.333. Okay, just goes on and on, 0.333. Now let's take the rates for, once we change up the concentration of N2, let's take the rates and see how that's affected. So then, if we have 28, and set it up the same way, right? Experiment 1 over experiment 2. 28 over 252. Get to 0.111. Again, is repeating out. Okay, so if we take 0.33 raised to the power of 3, raised to the power of 2, we get, if we have this squared, we end up getting this answer right here, right? And you could do the same thing if you were to reverse it, right? So if you did 4.65 on top, 1.55 on bottom, maybe this would be a little bit easier mathematically to see, right? So if that's going to be 3 right there. And then if you did 252 molar per second over 28, again, all I did was reverse putting experiment 2 on top. 252 divided by 28, and that gives you 9. So again, so this would be squared gives you this answer right here. So that must mean that N2, right, our x, turns out is going to be, let me erase the x here, maybe. And now that x is going to be a 2. So then we have our overall rate law, right? So it is second order with respect to N2, first order with respect to H2, and then our overall reaction order is third order, right? It's just the exponents added together, that's all. Overall order is third. So now that we have the overall rate law, the rate law for this particular reaction, right, we can actually use the data to calculate the rate constant here. The rate constant, or our little k, okay? K there. So if we could just pick any of the experiments, right? I'll just go ahead and do the first one, the first experiment there. So all you need to do is you plug in 28.0 into the rate, right? Into the rate, and then we have K, and then you have the concentration of N2, but we're going to square that, right? Since we determined that this is second order with respect to nitrogen, right? So we're just going to take that down here, carry it down to actually plugging in the numbers, right? So then we have 1.55 for the first experiment's concentration in N2, and then 2.10 for the concentration of H2. And again, because that was first order, we don't need to take it to the power of anything. Then we take 28.00 divided by 1.55 molar squared, 2.10 molar, right? So this is just isolating K here. And then K, that's supposed to be little k, is 28.0 divided by 1.55 squared times 2.10. Okay, it's 5.55 for our rate constant. Now, the tricky thing when it comes to rate constants in terms of the units with these guys is because your units will change depending on the order of your reaction. Okay, so notice here that I have molar per second on top, right? And then on bottom I have molar times molar times molar, right? So let me actually write that out. So if I have, let's choose a different color, molar times molar times molar, okay? So then if I have molar on top up here, I can cross it out with one of the molarities on bottom, right? So then our overall units end up being molar to the 2 minus, because I have 2 on bottom here, or the reciprocal molar, times reciprocal seconds. And this is the units, these are the units of K for an overall third order reaction. So now let's take all of the reaction orders, or 0, 1, 2, and 3, and we'll definitely stop at 3, and then write out what a sample rate law would be, and then what our units of K would be on for each of them. Okay, so if we have a reaction order that is 0, that is to say that the reaction rate does not depend on the concentration of any of the reactants. All it is our rate is going to be equal to K. Okay, so notice that we don't have any concentrations of reactants in there. Okay, so remember, the units of rate are just molar per second, so it turns out the units of K are also molar per second. Okay, so now let's talk about the reaction order, a first reaction order. That is to say that the rate only depends on the concentration of one reactant, some reactant A, whatever it may be, right? So then, if we are solving for K, the molarities, once you move this concentration of A to the other side, right, then our units just end up being, and the molarities cancel out, our units just end up being reciprocal seconds. And then once we have a second order rate, we can either have, and there are a couple of options here, right? We have rate could be k times a squared, right? Or the rate could be k times a times b. It doesn't really matter because either way you're going to have molar times molar right here, right? Same right here, molar times molar. So then if you're doing your rate, or molar per second, divided by molar times molar, then one of those molarities is going to cancel out, but then one molarity will be left. So you have reciprocal molar times reciprocal seconds for the units of K for a second order reaction. And then our last one is a third order, which we did previously, where we have the rate is equal to K a squared times B, for instance, and then we ended up getting molarity to the -2 times reciprocal seconds as well. All right, so that is, in a nutshell, how you determine the rate law from some rate data.